So, in modern climate change, we essentially started with the context for the modern climate change by looking at the movement of the continents since the last deglaciation started, movement of the ocean basin, how that affects the relative sea level change. We looked at the internal modes of variability briefly again, El Nino, Pacific Decadal Oscillation, North Atlantic Oscillation, and we will keep coming back to those because they are part of interpreting global warming, especially separating human impacts from natural variability. And then we have been looking at all the forcings. So, we will continue with the forcings and then get balance. We briefly mentioned radiation balance when we introduced climate, but actually for global warming we have to do this much more carefully. So, I briefly showed the carbon dioxide increases, and so we had to go a little bit into the carbon cycle for that, because we need to know where the carbon dioxide is coming from, where it is going, oceans, how they are changing, and now we will started to look at methane, another very powerful greenhouse gas. And we said the sources are the marshes, wetlands, and so on, where anywhere the organic matter gets buried and cannot be respired aerobically, the methanogenesis can happen. And also things like termites, cattle, or rice paddies, even the huge amounts of waters that are stored in dams for a long time can begin to emit methane, substantial amounts of methane. Okay. So, how has methane varied? If you look at the last few decades, methane has increased, but you can clearly see that maybe the rate of increase has begun to flatten, and this is shown again here as the rate of change of methane concentration in parts per billion per year, two estimates, and you can see that the rate of increase has in fact decreased. We don't know exactly why this is happening, but probably because the coal consumption has reduced. There is a large scale switch from petroleum to natural gas in many countries like the US, which found a huge source of natural gas, etc. Nonetheless, it's at least for now good news. In the longer context again, going back to 1,000 years, methanes have increased super since the Industrial Revolution, more than doubled to almost 1800 parts per billion by volume. So, we have to always keep going back to this context of longer time scales to see where we are headed. The N2O, which is again mostly from agriculture, is very hard to capture even in ice cores, as we will see going back to the Antarctic ice core. We will look at the figure we have looked at several times, but nonetheless for the recent times there is much more accurate measurements from the northern hemisphere, southern hemisphere, different estimates and so on, and you can see that they all show that the increase in N2O, again parts per billion, is quite steady as well, and we don't have a very good long term context for it. But going back to this figure, which is showing the ice core record going back to 800,000 years, we have looked at these changes in delta O18, which is an estimate of the temperature. We looked at the deuterium, which I haven't mentioned before, which is an isotope of water. So, I won't get into details right here, but that is another estimate of temperature, glacial extent and temperature. And here is methane, here is CO2, and here is N2O. And the point is that N2O is usually not as well preserved as methane and carbon dioxide. Various reasons for it, which we won't go into. So, what are we looking for here again? First thing is that context of the modern times for the levels of methane, carbon dioxide and N2O. They are increasing quite rapidly, but there have been rapid changes or so called abrupt changes in the past as well, right. We said it briefly that when glaciation happens, cooling begins to happen. So, as glaciers grow, albedo increases, more energy is lost, more cooling, more glaciers grow, but this begins to cool the global temperatures. So, the global humidity levels begin to drop because the impact of temperatures on humidity in the air is non-linear, it is exponential, there is a separate module to explain that. And that cooling and drying begins to make the snowfall rates smaller and smaller over time. So, as glaciers are building, the snow begins to decrease. So, the growth of the glacier begins to slow down, whereas when the warming happens, there is no such limitation. So, the little bit of warming, let us say by orbital forcing, happens, the albedo decreases, more energy is absorbed, more glacier melts, more albedo decrease. So, this can go very, very rapidly. So, you can have what are called abrupt changes, and the Younger Dryas, which went the other way, was an example of, on a short time scale, how you can have these fast time scale processes within the Earth system. These are relevant basically because in the context of forcing and the glacier melt, we are in the warming phase now, which is the fast phase. So, abrupt changes can occur, for example, begin to melt glaciers on Greenland or Antarctica. Obviously, the melting can accelerate and go very fast, and we will see some of these things in the modern climate change, but also they can have positive feedbacks from methane and carbon dioxide. The other thing to note here, we will come back to again and again, I have already mentioned this once, is that we are now increasing these greenhouse gases, whereas the temperature is still beginning to catch up. So, the temperature is not jumping up as fast as the greenhouse gases are jumping up. So, in the past, when orbital changes happened, typically radiation changed, temperatures changed, glaciers began to respond, and then greenhouse gases respond, whereas we are going the other way now. Orbital changing has not changed and orbital forcing has not changed. Temperatures are beginning to respond in response to the changes in greenhouse gases we are making. So, there is a time lag associated with that. We will come back to that, and there is a particular way to call that called committed warming, which we will get into. What are the other kinds of forcing we have? So, all these aircrafts that are flying around have substantial amount of water vapor and other carbon monoxide and so on that are being released and form what are called contrails. You can also see these for ships, for example, as they slowly drift along in the huge oceans, they create a contrail. And these contrails actually can reflect large amounts of outgoing long wave radiation back to the surface and can have a substantial forcing of the climate. There are some ideas that if we switch the height at which the altitude at which the aircrafts fly, if they are reduced and brought down by a few thousand feet, so go from 31,000, which is the average now, down to about 24,000, then the formation of these trails becomes harder because of the differences in the weather and the temperature gradient and so on. Of course, as you come to a lower altitude, the density also increases, which means the drag on the airplane increases, which would increase the fuel consumption by about 4%, but there are some calculations done to show that that increased drag and fuel consumption more than compensated by the reduction in the contrails and global warming forcing. So, that is something to keep in mind. There is a trivial fact that is not so trivial, I should have pointed out here. Termites, what do? They basically consume hydrocarbons and they produce methane. So, obviously, they get into the house. If you have wooden stuff, that can be a big problem, especially in continents like America, where they build houses very quickly with wood rather than brick and cement like we do. They always have to watch out for problems. But on a long time scale, termites have had a different impact. All this hydrocarbon that was getting formed and buried, which is being converted to petroleum, natural gas, methane and so on, actually has been forming at a much less rate or has not been forming as much since about 120 million years when the termites evolved. So, the termites live under the ground, and all the hydrocarbon that would get buried and become eventually coal, gas or petroleum has been consumed by the termites. Just some trivial fact to remember. Okay. Going back to the forcing, of course, we still have to keep in mind the solar forcing and the volcanic forcing. I will show a figure again. But the important additional point I want to make here is that now we have satellites going out of the atmosphere and looking at the radiation coming in. So, unlike before where we relied on historical documents or count of the sunspots and measurements of radiation and relation between sunspots and radiation, now satellites give us much more accurate measurements, and you can see that there is very high frequency measurements from satellites, and they correlate with sunspots, not surprising, which we already knew. So, the idea is that more the sunspots, more the solar irradiance, which we have said before. As sunspots are reduced, radiation is reduced because of this plage around the sunspots, and there is an 11-year cycle. So, we will keep coming back to this. The volcanic forcing has varied time, and the solar variability continues to be dominated. The other important forcing from human activities is the so-called aerosols. So, this is showing an animation of satellite data of all the particles in the atmosphere that reflect any kind of radiation back to space that satellite can look at and assign it to clouds versus humidity versus dust particles or any particle that is called an aerosol. It could be actually microbes, it could be dust, it could be coal burned products, ash from volcanoes, and so on. And this is model simulation of the dust coming off of Africa. You can see that it's getting carried and even becomes part of the hurricanes as the hurricane gets deflected and goes northward. So, there is a lot of interesting physics here that relates to how the dust in fact affects hurricanes. We mentioned briefly that aerosols affect cloud condensation nuclei, cloud brightness, and cloud droplet sizes, more drizzle versus heavier drops. So, this is a big impact on monsoon, for example, but there is some knowledge now to also explain how aerosols in fact affect hurricanes. So, this is now a very new research area, but we are learning more and more as we go along. So, aerosols are a very important forcing being increased by human activities because of deforestation, urbanization, agriculture, and in general drying in various regions. And obviously, it changes from year to year because of things like El Nino as well, because El Nino introduces droughts and floods in various places. We will see again later on. The other things that also are part of the aerosols, mostly product of coal burning, are so-called sulfate plumes. Immediately you can see where the bull's eyes are. Obviously, they correspond to high economic activity, high power production by coal burning and so on. So, US, where the coal plants are, US has very systematic so-called coal bans from West Virginia, south from Alabama into Pennsylvania and so on. Europe is still burning substantial amount of coal or generating sulfates from inefficient burning of fossil fuels and so on. And China is obviously another bullseye where high economic development produces lots of sulfates. And we will see what sulfate forcing is, the radiation balance of the earth. So, lots of different types of forcing. So, how has sulfate concentration varied? Going back to about the 1600, we can look at the sulfate emissions from volcanoes. Volcanoes put out a lot of CO2, but also lots of just ash and also lots of sulfate, carbon monoxide, methane, and so on and so on. So, the range of natural emissions is shown here, and since industrial revolution, the human emissions again have gone beyond, well beyond the range of natural variability of sulfates. So, this is a significant forcing on the climate due to human activities. As you can imagine, the lovely pollution we can see everywhere. You can guess which country this is. There are some kids playing cricket in this very nice clean weather, and that's generally called brown cloud. Appears as a brown mess from aircrafts or drones or satellites. And this was discovered more or named more specifically as brown cloud in the 1990s by an Indian scientist, well-known radiation and climate scientist called V. Ramanathan. And he first named it Asian brown cloud, and then it turned out that it's all over the place. I think Indonesia, Hong Kong, it's all over the LA area in western US, for example. So now it's more generally called just brown cloud and not the Asian brown cloud, because Asia is not so special in producing pollution. But this pollution affects monsoon and so on, which we will see later on. So let's try to visit this now as a combined radiative forcing of the climate system and try to add additional information and come back to energy balance, because I will show that energy balance has been explained in a simple way, which is good, but as a teacher you want to be aware of some of the details so that you can choose how much of the detail to explain to the students and how best to do it. It turns out that it is not that simple. So to put together, you start by looking at the radiative forcing. Positive means they are keeping more energy in the system. Negative means they are creating more loss back to space. So obviously things like CFCs and greenhouse gases like N2O, methane and CO2 add to the energy being trapped, and you can see that CO2 dominates obviously quite a bit, more than 1.5 watt per meter squared. You have to get that is. So if you remember, the net energy received is around 240 watts. This might seem like a small thing, but it begins to get amplified because of increased temperature leads to increased water vapor, which is a strong greenhouse gas, and that increases temperature further, which can melt glaciers, which can reduce albedo. So you can have all these internal feedbacks which can amplify the forcing because of greenhouse gases. Ozone, we know that it's a good thing when it's in the stratosphere because it reduces UV that comes to the surface, which is harmful to all living things, and that actually absorbs the energy because UV is being reduced, oxygen molecule is split, combining it another oxygen molecule, endothermic reaction. So the stratospheric ozone is good in all ways, including reducing radiative forcing of the climate. But because of all the fossil fuel burning, we are also generating significant amounts of ozone in the troposphere, which is a very nasty gas. If you breathe ozone, it is very harmful to you, and it has greenhouse gas forcing. It's a positive forcing. It creates more energy trapping. And going to sulfate, sulfate is actually bad. Coal burning, coal smoke is actually bad for your lungs, but it scatters radiation, so it makes you lose the energy to space. And a good thing? Obviously not, but there are so-called geoengineering experiments being thought of, where you go into the stratosphere and you spray some kind of an aerosol to reflect more sunlight, like sulfates, which are highly reflective. They can stay there for a long time. Of course, they will eventually rain and do some acid rain and so on. So it has to be done carefully, but it looks like it will be tried sooner or later because it seems like somebody will do it. Probably worth trying. The problem, of course, is that reducing incoming radiation doesn't mean that you are reducing the heat, because if we are still continuing to emit carbon dioxide, when you stop doing the aerosol injection in the stratosphere, again you will be back to the square one, or you will again have global warming continuing, and things like ocean acidification, as we will see, will continue even if you do geoengineering like this one. I just wanted to mention that, a bit of a digression, but nonetheless. So black carbon, again harmful to us. If you breathe it, it's going to get lodged in your lungs, can be very bad. If you have lots of children having more and more asthma in cities related to pollution, ozone and black carbon and so on. Black carbon is very strong absorbent. Anything that's black is going to absorb radiation, so that is providing a positive forcing, whereas organic carbon on the other hand can be a reflector or a scatterer of radiation, can be a small reduction in global warming. Again, not a good thing overall, but just looking at radiation, it has a reflecting effect. Biomass burning, which is basically these large scale crop residue burning, chulas, any kind of wood burning for cooking, etc. As we know, in India, indoor pollution is a big problem. Many women end up with serious issues, health issues because of that. And there is large scale burning for slash and burn kind of agriculture. You can see plumes of smoke from large scale crop residues burning from places like India, Indonesia, Africa, various countries in Africa, South America, and so on. And in fact, in 2018, there was massive dust storms and combined with all this crop residue burning. So seasonally, Delhi area every year has huge pollution problem because the land is being cleared for agriculture prior to the monsoon season. Aerosol indirect effect, that is its effect on cloud properties and rainfall. We don't know exactly whether that's a positive or negative, because aerosols, there is some evidence showing that they can increase the reflectivity of the clouds, which means top of the clouds can lose more energy, higher albedo, but if the clouds are thick, they can also absorb outgoing long wave radiation, which means during the day they may be reflecting, but at night they may be trapping the outgoing long wave radiation. Effect is not very well known. Land use, the albedo change because of changing the types of vegetation or urbanization increases the albedo. It says albedo only because it also has an impact on CO2, which we looked at when we looked at the growth of land use contribution to CO2, right. So, just the albedo part of it tends to cool the earth, and the solar variability itself in the anthropogenic time scale has been adding, and it is pretty small compared to all the greenhouse gas forcing. So, this is something nice to remember. Thing that's shown here that's important is that the understanding of various forcing is high for greenhouse gases. For ozone, we know a lot, but it's kind of medium, and sulfates, the understanding is low. Black carbons, it's quite low, but as we go forward and collect more and more data from the ground stations and satellites and drones and balloons and so on, these understandings will continue to increase because the focused efforts to collect data to understand radiative balance is growing in urgency. But there is another problem with it. Even if the understanding is high, doesn't mean that we can use it to make better future projections, because future variations are not always clear, and to include aerosols in models is still kind of a challenge, because the model is trying to do global circulation, tens of thousands of kilometers, and it has to also worry about this molecular level interactions, particles and humidity and radiation and so on. So, to cover these wide ranges of scales is not very easy. Okay, that's something to remember. So, this is a good picture because it shows all the radiative forcings of the anthropogenic era and the level of scientific understanding we have right now. Let's look at it in another way, where we look at the same things and separate somewhat the human activities from natural processes, but also look at the kind of residence times of things. So, you can never get tired of looking at these, because the more you look at it, the more comfortable you will get at what are the issues we are dealing with. And this also shows what is the net human activities effect on radiative balance at this point. So, going back again, CO2 is high, more than 1.5 watts per meter squared. Methane, nitrous oxide and halocarbons together about 1 watt per meter squared. These are increasing. Remember, we looked at CO2 continuously growing. We said methane had increased and now has flattened, but whether it will come back or not, unclear. N2O is increasing. Halocarbon dynamic is changing because we replaced CFCs with HFCs, but we know that HFC is in fact much worse for global warming than CFC. It's good for ozone hole, in the sense it doesn't destroy ozone like CFCs did, but it's worse for global warming. So, now the race is on to replace HFCs. By 2030s or so, all countries have committed to replace HFC, and there is a human dimension to it, in the sense as countries like India warm and the demand for air conditioning keeps going up, what will be replacing HFC, who will own this product, how much it will cost, and how that will affect our commitment to reducing our carbon emission and so on. Okay. Stratospheric ozone, tropospheric ozone. So these are typically long lived, especially CO2. I will have a table of residence times in a minute. Stratospheric water vapor, which was not in the previous figure, there is evidence now that the stratospheric water vapor is increasing. The physics of it seems to be that with global warming, the so-called lapse rate we looked at, so the temperature versus altitude looks like this. This height increases, which has something to do with radiative balance, which I will get into in a few minutes. So increased stratospheric water vapor is bad. Ozone is good, but water vapor in the stratosphere acts as a greenhouse gas, and that's not a good thing. Land use, an additional thing mentioned here is black carbon on snow. So as emissions are increasing, especially in regions like the Himalayas or the Alps where human activity is high, and even you can find human imprint on snowfall over the far corners into the Arctic and Antarctic regions, black carbon is absorbing, so it increases the warming within the snow and increases the melt rates. Bad news. So that is mentioned here. Total aerosols, again we said the understanding is low, uncertainty is high. So these you can see that these are uncertainties. So the cloud albedo effect of the aerosol, it's estimated to be here, but you can see that the uncertainty is 3 times higher. So that means the understanding is quite low. Radiation we know very well now because of satellite measurements and so on, and it seems to have a systematic 11-year cycle, which is good, and that has a small positive forcing, so it's not a big contributor compared to greenhouse gases. So the net effect is that altogether the force in the human era is about 1.5 watt per meter squared. This is from 2005. So by now this has already increased by a little bit, and it continues to increase. But there are some good news like reforestation, greening of the earth, which is going to help in terms of absorbing and reducing the radiation forcing from anthropogenic activities. So here again looking at something we looked at before, over time the emissions from solar is basically somewhere little bit small one here. Black carbon on snow and contrails, it has other well mixed greenhouse gases, tropospheric ozone, stratospheric H2O and so on. So that goes up to about 2005 here, and year 11 is shown in contrast, and you can see that the ranges are already increasing. So every forcing is automatically increasing over time, and the total anthropogenic forcing at any given point can appear to be negative because you may have more or less volcanic forcing, which is not easily predicted. So volcanic forcing obviously is important and can locally produce cooling, but we have to always consider this as part of the overall effective radiative forcing of the Earth system. So the aerosol radiation and aerosol cloud interactions remain remarkably big challenges for modeling and for observing, because the dust is very local. Even though the animation we saw of African dust getting carried away to all the way to America is a large scale thing, but it will be in pieces, it will be in small chunks. So modeling and observing these are not easy. So let's get into a little bit more details on energy balance. We looked at all these forcings that are creating radiative perturbations for the Earth system, and you probably heard already several times, including in these sets of lectures, that in a natural greenhouse effect it's a good because it has given us the temperature which probably played a critical role in keeping water in all phases, ice, vapor and water liquid form, and that probably helped life to evolve here. And in that case the solar radiation albedo reflects some and rest of it heats the atmosphere and the surface. outgoing long wave radiation or thermal radiation is reflected back. And the greenhouse gases that occur naturally modulate the surface temperature and give us a nice comfortable temperature, even though it ranges from -50 over Antarctica to +30 over the tropics and so on. The average temperature is very nice, and this is often referred to as the Goldilocks Syndrome. It's a perfect blanket. So if you look at Venus, 460 degrees at the surface, Mars -50 degrees centigrade at the surface, Earth a nice 15 degrees centigrade in the global. So this is a Goldilocks syndrome, too hot, too cold, just perfect, right? And we say that human induced greenhouse effect is essentially keeping more of the energy and less heat escapes into space. This is okay for explaining at lower levels, maybe at high school level or so, but once you get into higher levels of education, you want to be a little bit more careful about it. The thermal radiation was discovered by Herschel, William Herschel, in the early 1800s. Joseph Fourier then took the system and realized the incoming short wave has to be balanced by outgoing long wave. Svante Arrhenius then realized in the 1870s that increasing carbon dioxide is basically trapping more heat. So we always keep saying trapping more heat, but does that really mean that less heat is escaping to space? Not really, because the radiation balance still has to happen at the top of the atmosphere. It's a question of at what temperature this balance is now happening and how a radiation balance is possible at a different temperature when you increase greenhouse gases. So as a teacher, let's say you drop the tectonic time scale climate change, which released a lot of time for you, then you can spend more time on doing radiation balance, which is much more critical. But this physics is quite complicated. There have been very big names working on this problem, including Planck and Heisenberg and all the big names, Einstein, everybody worked on this problem. So let's look at a simple balance and make some additional points which are critical. So you must spend as much time as you feel comfortable to understanding as many details as possible so that you can explain it in a clear way. So this always takes me a long time to arrange this information in a way that I can explain in more detail, but without getting into the gory details of radiation physics, which is very complicated. How do we do that? Let's go back to radiation, and the Earth receives it so far away that essentially the rays are parallel by the time they reach Earth. Earth is a sphere, so sun's radiation would create a circular shadow, which means if you hold a volleyball or a basketball and shine a torchlight, it will create a circular shadow on the screen behind. So that is the area that is intersecting the radiation, except that Earth is rotating, so we have to always remember that. So the net energy intercepted is the solar constant, so that is energy at the top of the atmosphere multiplied by the area of the circle which is intercepting it, that is that number. Immediately you know that there is an albedo, so you have to subtract that part. So the albedo is about 0.3, so 1 minus 0.3 will give you 0.7. So 0.7 of that is this number. So that is the net energy that is coming into the system at the top of the atmosphere. We already saw that atmosphere absorbs some, lets some to the surface, and so on. Anything that is coming and heating is going to be reflected as thermal radiation, which is given by the Stefan-Boltzmann law, which is just the Stefan-Boltzmann constant times the emission temperatures to the power of 4. Very simple formulas, sigma Te to the 4. So that is the radiation per unit area. Each unit area that's getting heated is emitting that much radiation. Entire surface of the Earth is emitting, so we have to multiply that by the surface area of the sphere, So, that is 4 pi a squared. A is the radius of the earth times per unit area. So, the energy received, energy emitted. It is very easy to say, and in fact, you can plug in the numbers, invert this relation for TE. So, equate this to this, invert for TE, compute the Earth's emission temperature as the solar constant 1 minus albedo divided by 4 sigma. That will give you 255 K, which is minus 18 degrees centigrade. Is that the average temperature of Earth? Of course not. Why? Because we have not included any greenhouse effect at this point. How does that work? So, here is again, now we are, instead of looking at the whole Earth, we are looking at 1 square meter of the Earth. Just it's easier to do it this way when we want to get into the black body effect and the atmospheric greenhouse effect and so on. So, there is again, when you divide the pi a squared times S0 1 minus alpha, distribute it over the whole surface because Earth is rotating, you will end up with 1 over 4, and albedo is going to lose that much. So, the surface receives S0 minus alpha S0 divided by 4. That is going to heat the surface. So, we have assumed that the atmosphere is completely transparent to the short wave coming in. So, all the short wave, what is reflected is going to reach the surface, and we are going to assume that the surface is going to emit some long wave and some short wave back. So, the emitted short wave is here. The emitted thermal radiation or infrared is going to hit the atmosphere, which is not transparent long wave unlike short wave in the simplistic model. Why? Because it has greenhouse gases. So, any greenhouse gas molecule is transparent to a photon of energy in the short wave, it lets it go, but the photon of long wave energy coming back from the surface excites the rotational mode or the vibrational mode in it. It is too weak to create a translational mode, but if you do not want to know those details, it is okay. Basically, they absorb the energy photon of light in the thermal band or the infrared band. Remember, you have the violet, indigo, orange, blue, etc. That spectrum you have to always keep in mind, and red is at the long wave or the infrared end of things, violet is on the other end, short wave. So, the thermal energy is on the long wave end. The CO2, CH4 and other greenhouse gas molecules are susceptible to these photons in the. So, they absorb it and then they radiate that energy in every direction. So, back to the surface and out to space. Very simple, not very complicated. You can just look at this again and again. Short wave coming in, long wave heating the surface, thermal radiation going back is going to be affecting the atmosphere, which itself will begin to radiate thermal radiation in every direction. So, it is putting something back towards the surface and something out to space. How do you do that balance? Basically, you look at, so here it is explaining why we have divided by 4. So, the circle we looked at is pi a squared, but that circle is rotating because Earth is rotating. So, the area that is actually intercepting the total radiation in a day 4 pi a squared, that is where we get the 4. The emission from the surface of long wave radiation is basically the atmospheric temperature multiplied by the Stefan Boltzmann constant. So, the long wave radiation emitted by the atmosphere into space and back to the surface is sigma T to the 4th, where T is the atmospheric temperature. Okay. So, that radiation coming down has to be equal to the net energy. So, you have surface receiving this much short wave and the atmosphere is losing to space this much long wave. So, those two have to equal each other to have balance. Okay. So, instead of calling this atmospheric, we typically call it the emission temperature. So, that is sigma T e to the 4th. Essentially, that is sigma T a to the fourth if one layer of atmosphere. Things get complicated, so let's keep adding little by little. So we're just doing very simple energy balance where incoming short wave is being equated to outgoing long wave, because that is the balance that must work. So now you remember the atmosphere is sending radiation in this direction and in this direction. So the downwelling long wave radiation is the same amount as outgoing. We have only one layer, which means near the surface net thermal radiation has to be the surface temperature times to the fourth times sigma. But this is the net impact of short wave heating it and the long wave from the atmosphere heating it. So the surface is getting short wave, which is equal to this amount, and it is getting long wave from the atmosphere, which is that amount. So the net surface temperature is determined by the sum of those two things. So that means the net outgoing long wave from the surface is the short wave that's coming in from the sun and the long wave that is coming from the surface. Unfortunately, we used S here, that is the outgoing long wave from the surface, not solar radiation. Solar radiation is S0, which is a constant at these time scales. So now equate the total energy to S is to the fourth, which is equal to this, and coming down is sigma TE to the fourth. So just this is again equal to the same thing, right? So put that in. So you essentially get sigma TS, the surface temperature over R, outgoing long wave radiation, is twice what is emitted by the atmosphere. So if you simplify this equation, this is a very important result. The net effect of greenhouse gases is that the surface temperature can be warmer than the emission temperature. Atmosphere is emitting above at a colder temperature, but the net effect is that internally you can bounce energy back, take the incoming short wave, take the long wave from the atmosphere and create a surface temperature that is warmer than what is being emitted to space. This is very critical. You should get this concept very firmly established in your mind so that you can explain it properly. The net effect of greenhouse on Earth is you can create a warmer surface temperature. The best analogy you can use is that you are cold and you are putting a blanket over yourself. Your body temperature is 98.2 or whatever, but if you cover yourself, within a few minutes you can trap that body energy and create a temperature that's much warmer. So without any heater, use your own body heat and feel warmer, because you are keeping the energy that is going out from your body. So that's something like what is happening here. The so-called blanket of greenhouse gases is making the body warmer, so that surface temperature is getting. This gives us the right greenhouse gas. We will come back and see that this is still not enough. This gives us much warmer temperature because the atmosphere is not just one layer. So we will add the additional details in the next part of this lecture, but this part of radiation balance you should learn step by step. So then you decide how best to include it in your course as far as the details are concerned. So you must build a mental model that allows you to explain clearly beyond the simple idea of greenhouse gases allowing energy loss to space. How can you realistically explain actually what's happening? Okay, see you next time.